guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in mathematics, of course, which comes from the broader topic of power and logarithmic functions. But this is going to deal exclusively with the concept of power functions. Now that we have looked in some of our videos about the concept of exponential functions and logarithmic functions, this is going to be just a basic information to assist us in case we come across the concept of power functions. We can be able to express them in a way that is, of course, required or demanded of us. So for that case, thank you and welcome. So as I've said, today we're going to look at exclusively on the topic of power functions. Just this spiral, just going to use. We're going to look at exclusively the concept of power functions. And these are basically exponents which are expressed using different terms. Now, this is different from other topics that we have discussed, especially on the exponential functions, which we basically dealt with on how we can be able to express them as logarithms or vice versa. So in this case, we're going to look at different ways in which we can be able to determine, identify, and trying to treat these power functions. So in this case, by definition, power functions refers to functions where the independent variable occur as an index or as a power. So in this case, of course, we know that from an expression, we can have an independent and dependent variables. So in this case, from the term independent and dependent, of course, we're going to know that one variable will exclusively depend on another one to be expressed, but there's another one which can vary without a degree of limit. So in this case, for the power functions, these are functions where the independent variable occur as an index or a power. So for us, in expressing the number or the quantity, or writing an expression as an index or a power, we are given it as such whereby these numbers can be integers. So in this case, this one can be a positive or a negative one. And in this case, we're going to see that these power functions, a function is expressed as a quantity like that. So these power functions can be expressed as integers, as we said. Now suppose I write a number like 2 raised to power x, then therefore that is going to represent a power function. So this can be maybe 6 raised to power 8, etc. So this one's can be expressed in terms of numbers. Now in this case, if we have a function like 2 raised to power n, and n is a positive integer, whereby n is a positive integer, then we can be able to define other quantities, maybe which can be expressed in terms of this number and n. And suppose n is a negative integer or vice versa, then given a number like 2 raised to power n, and as we have said, n is an integer, therefore can be a positive or a negative. So in this case, given a number like this, we can be able to express it in terms of 1 over 2 raised to power n. So similarly, if given a number like 8 raised to power negative 3, we can be able to express it as 8 raised to power 3. So in this case, provided that the number, this one which is 2, now suppose I write a number like x raised to power negative n, provided that x is not equals to 0, then we're going to have to express this number as I've shown on these two examples by finding the fraction of that number or expressing it in terms of that ratio. So in this case, of course, we will have a general definition for that particular expression, whereby we have that number a, whereby we have said there is a condition that a is not equals to 0, and we are given a number like a raised to power negative n, then we can be able to express this one as 1 over a n to the power of n. And therefore, in this case, this one leads us to some of the specific rules that we are going to see. And these rules are going to apply across maybe all the operations or arithmetic operations that we are going to do for integers. And partly they're going to have a relationship with some of the logarithmic functions that we have discussed in some of our videos. So suppose we have a number like a raised to power n, and we're having a product a raised to power n. This is m and n. Therefore, this is going to be expressed as a m plus n. So given that these numbers are the same and then they are raised to different integers that we have written on the board, and we're going to have the sum of those powers expressed, that number expressed as the sum of those powers which it has been raised to. So therefore, we have seen some of the concepts in some of the similar concepts that we have discussed in logarithmic and exponential functions. And in this case, we're going to learn about the concept of maybe associative, distributive, and other laws. So in this case, we have out of the power rules, the power of powers, powers of exponents, etc. So in this case, if suppose we have a different number like that, then we're going to have a product of those exponents, and the number will be expressed as a m n. So in this case, even if the number is m and n is not is a negative or a zero number, these two basic procedures are going to apply in that particular case. So in this case, if we try to look at a sample question to assist us understand this concept about the power functions, we can therefore be able to look at a number like this is 2 raised to half squared, and therefore this is going to be expressed as 2 raised to a half times 2, which is going to give us 2 raised to power 1, which is 2. So in this case, this is the first, the second law where power is being multiplied by another one. Then we're going to have that our power is being multiplied by another one, and then we're going to see that under different places. Of course, if there were two different places, as we said, like a m times a n, then therefore this is going to be a m plus n. But in this case, whereby there's a direct multiplication of powers, then we're going to use this specific concept to find the value of that number. So therefore, in this case, we can define this one as, if the value of this one is 2, therefore we can define this one as the root of 2. So in this case, we're going to see that numbers which are expressed in a similar manner are going to be, okay, let me just give that one by an example. So if a number is expressed in that way, then we are definitely using this analogy, we're going to express it using that kind of an expression. So suppose we have another number, we're just going to do a comparison so that we can come up with a general statement on how we are able to apply that specific rule. So suppose we have a number like 2 over 3, and then this one is raised or cubed. Therefore, we can express this number as 2 over 3 times 3, which is going to give us 5 squared. So we can be able to define the function, all of this function as if we try to look at this number that we're trying to express as a root, maybe a square root, cube root, etc., it is this specific fraction of this number. So we're going to have the root of 5 squared. This particular exponent for the fraction is going to be maintained. So in this case, we're going to have this number expressed as such, the cube root of 5 squared. So more generally, we're going to have a number whereby we give a condition that if it's a number a and a is not equals to 0, which has been expressed as a is given as a p over q, whereby p over q is the exponent that we said, and this number has been multiplied by q. Therefore, this is going to give us a value of a raised to power p. therefore we can define a, okay, let me remove this one from here. So therefore we can define a as so we can define a p over q as p. I mean this is q, the root of a p. So this general definition stems from the fact that we have been doing these two examples for 5 and 2, the first two that we had given. That was 2 raised to the exponent of half into brackets squared. So in this case, of course, for 5 raised to the exponent of 2 over 3 cubed is going to be expressed as this. So generally, assuming that a represents this number that is 5, of course it has been raised to an exponent of p over q, then we are going to multiply by q is going to give us that value. So this basically tries to imply the order of operation that is taking place between the exponent and the power that is expressed outside there. So this number can be able to be expressed as that. Therefore, we extend this particular expression can be extended to powers that are negative functions, provided that, as we have said from the previous discussion, a is not equals to 0. So then, given an expression which has got a negative exponent, and we can be able to express it using this general formula by using this specific procedure. So if we have 4 negative 3 over 2, then we're going to express this one as 1 over 4 3 over 2. So in this case, if it's a negative exponent, then if we express it as a fraction, that negative exponent, also as a reciprocal, that negative exponent disappears. So in this case, as we can see from this, still we can be able to simplify that and try to express it in the order that you have said. So if this is the, as I can refer it, the numerator part of this fractional exponent, and we're going to write it as 2 the power of 4 cubed. So in this case, as we have said, we normally express it in terms of a fraction as such. So I've just done a simplification of this, the denominator part of that fraction, and that will be the value there. So still we can be able to simplify the last part of the expression, and then we'll have 1 over the root of 4 by 3, this is 64, and therefore what we're going to get it's 8. So this is using the basic concept that we have defined for power functions for both negative and positive values. We can be able to find the value of this quantity by trying to exploit that procedure using the law by taking this one as the root of that quantity which is given over the product over the exponent of the numerator together with this value that is a general a that we had given. So therefore we're going to express it in this term and find that the answer is going to be an 8. Now this relationship that exists between these two different values that we have expressed is true for all rational numbers of course the m and n that we had defined in these specific examples that you had given. So the application that we have talked about is true for all rational numbers of m and n, whether they are positive or negative, integers or fractions. So as we can see that first we had given integers and second we had given fractions, and generally we had used the positive value and the negative value, and we have seen that this general law is applicable for all rational values of m and n, whether they are negative, positive, integers or fractions. So this is how we apply the power functions, and generally if we come across it, then we can be able to remember this specific procedure or laws that we have mentioned, which apply to power functions in as far as their values are concerned. So in that case, that's the end of today for the topic of power functions. I hope this is going to assist us, of course, bearing in mind that we have seen the relationship between indices and logarithms. This is also going to apply and affect some of the laws that we have discussed under these topics that I've mentioned. So in that case, that is it for today, guys. Bye. God bless.